Okay, thank you very much for the invitation and for staying here. So sometimes people say I'm the last obstacle for lunch, before lunch. So I will try my best to make it as smooth as possible. So here I'm going to tell you about another way of thinking about another way of an approach to quantum non-locality that is also useful when you want to consider quantum non-locality. By quantum non-locality, I mean the violation of the Bell inequality that has been discussed here for information processing. So I'm working at ICFO and I lead the quantum information theory group. So I care about how to use quantum effects to solve information problems in ways that are not possible classically. Okay? But when you look at, if you have ever looked to quantum information applications, usually they are never based on violation of Bell's inequality. So usually they are built on entanglement or superposition. And for me, this was somehow, well, I wanted to understand why this was like this, okay? Because, I mean, in the end, the only reason why the point where we realized that quantum physics was different from classical physics was after George Bell, okay? Because then, before that, there could also always be the possibility of an EPR model for the data. This was a logical, valid possibility. And it was only when John Bell derived the Bell inequalities and he showed that these inequalities were violated by quantum physics that we understood that there is an experimental difference between classical physics and quantum physics. Still, I mean, in principle, quantum information theory is a theory where you want to do things that are different from what you can do with classical information theory. But we never seem to use a Bell inequality. Okay, so this was somehow something that was leading my thoughts from time to time, and I think now we have somehow find some sort of quantum information theory based only on non-locality, which I find in some sense more satisfactory, and you will see it gives you some advantages for information processing. And what's this? This is something that is sometimes known as a device-independent quantum information processing. So it's a sort of new approach to quantum information theory where you deal with your devices as black boxes. Okay, sometimes we also call it as quantum information theory with black boxes. So in all my talk, you're going to see just boxes. Okay, so what I mean by boxes is I'm a user and I go to a provider and I buy a device, and what I get from this provider is just a box. Okay, the provider will tell me, here there is a spin 1/2 system and you make this measurement and blah, 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 blah. But what I get is a box. Okay? And this is what I want to show here. So here there is one user that gets one box, there's another user that gets another box, another user gets another box. And this user has, you can think of this box having different buttons. And you can press one button, another button, another button, another button. Or you can simply feed the box with classical information. Okay, you do whatever you want. You press buttons. And then I label this action on your box, which is something macroscopic that you can really put on a piece of paper. You can write, I press button 1, and then button 2, and then button 100, and so on. This is something that you can do. And then as a result of you pressing the button, the box gives you an output. Okay? So, I mean, this is very minimalistic, but if you want to think about a realization, this is just, you prepare a state of many particles, you make different measurements, and you get different results. Okay? So the choice of your measurement is the X, and the measurement result is A, but you can see it in a more minimalistic scenario. You can see it as me pressing a button and getting an answer. And you see here, just a box where I can perform a classical action and I get a classical action. And the description of my devices are given by what I'm going to call the observed correlations. So I can take these boxes, I can press buttons, I can collect the results, I count the frequencies, and at the end of the day, I can estimate these numbers here, which are the probability of getting result A1, A2, AN, when I press button X1, X2, Xn. You understand that to estimate these numbers, you don't need any modeling. You just get the boxes, press buttons, observe outputs. Okay? I don't have to make any assumption about these devices. This is why it's called device-independent. Okay, so what is device-independent quantum information processing? You want to do task for information in task. You will see cryptography, for instance, only based on the observed correlations. And what you will see is that if you want to do things that are interesting in this scenario, it's better for you that these correlations violate the Bell inequality. Okay, so in this scenario, by the way it is defined, you need data that violate the Bell inequality. Otherwise, these devices, you can give them back to your provider and they are useless for you. Okay. So why someone can do this? I mean, in principle, if you think about this, it seems very minimalistic and too simplistic description of the scenario, okay? Because I can think of anything here, okay? Just I can put any, what is this correlation? These are just positive numbers because they describe probabilities, and that they are normalized. When I sum over the results, the sum of the probabilities have to be 1. So they seem pretty innocent. I can put whatever I want there. But, okay, most of us here, we are physicists, and we understand that if we have some devices, they can be arbitrary, but they will satisfy some physics principles. Okay, so I don't know, there are things that we don't think that devices will violate. So I will give you the simplest principle that most of the people agree with, okay, which is no similarity. So I can think of these devices that I have one, Armando has another one. They can do whatever they want, but probably they won't allow me to send information faster than light to Armando. Okay, so most of the people here will buy the assumption. If me, I'm going to buy it. Okay, so I will assume that these devices can do whatever they want in the process of producing the input, given the output, but I won't be able to use these devices to make information travel faster than light. And this is something very simple. This simply means that what I see here cannot depend on what Armando chooses to measure here, because if it was the case, Armando, by choosing a different button, he could signal to me. So this is what is called the non-signaling principle, and this simply means that what a subset of the parties sees, so you see here I'm summing over the results of parties k plus 1 up to n, so I'm summing the result of some of the parties that have devices, does not depend on the inputs of these parties. Okay, so if you, in the simplest case of 2 parties, 2 devices, what Alice sees cannot depend on what Bob measures. Okay, well, this is mathematically tells you that this object that I defined before has to define these linear constraints. Okay, so you can put any numbers there, but not any. Okay, so these are defined the set of non-signaling correlations. Well, then there are some other correlations in nature, and these are the standard classical correlations. So here, in these classical correlations, what you have to think of, these devices have been built by a provider. No? The provider built all these boxes, and what this provider did, he put some a classical computer given the producing the output given the input. So you can think of just a computer that gets the input you're going to measure, looks at the program, and depending on the input and the program, gives an output. So this is the program. Okay, this is a function that computes the output inside the box, given the input to the box and the program. And you combine these different programs, and it gives you the classical correlation. So these are nothing by the standard EPR, Einstein-Podolsky, and Rosen correlations. But you can think operationally, I mean, operationally they have a very concrete meaning. So it's all what you can do if you think about some classical instructions within the devices. And of course, we know that there are some other correlations. There are the ones that you can obtain by measuring a quantum state. So what are quantum correlations? This is just the numbers that you can write as the trace of a quantum state and a measurement in the first device, tensor product, a measurement in the second device, tensor product, a measurement in the third device, and so on and so on. Okay? So these are quantum correlations. So here, I'm not saying anything about the dimension of these objects. Okay? They can be states of dimension 2, 3, 4, infinite. But what is clear is that if some correlations are quantum, there exists a Hilbert space where I can define a state and measurements, combine them, put the trace, and give me these numbers. Okay, so this is, you understand that if I put some physics into the picture, I cannot have any numbers here, but they have to satisfy some non-trivial numbers. Okay, and what we know is that these sets of correlations, if I have this hierarchy. Okay, so the set of classical correlations is here. Okay, I mean, I'm not going to, it's a convex set, it has some mathematical properties, doesn't really matter. So there's a set of classical correlations here. And we know that the set of quantum correlations is larger. Why? Because quantum correlations violate a Bell inequality. Okay, so the set of correlations that I can achieve in classical physics is the one here. And there are some boundary that are the Bell inequalities. And whenever I violate a Bell inequality, I have some quantum correlations that do not have a classical explanation. And this is why the set of quantum correlations is larger than the set of classical correlations. Okay. But what we also know is that in principle, you could define some numbers. I could give you some probabilities that they look as normal probabilities. They don't allow any fast-like communication, but they are not quantum. Okay, so you will see that I can give you some points that they look very innocent. You could expect finding these numbers in the lab, but if you were able to see these numbers in the lab, you would be falsifying the whole quantum physics. Okay, so this you will see why this can happen. Okay, so this is, again, all my talk is going to be about boxes, correlations, and this set of classical quantum and dimensional correlations. Okay, and again, remember this is what I want to do. And this scenario is very good for situations where you want to, where you have problems with certification and trust. So usually this is very good for cryptography. I don't know if you were aware of this Snowden case with NSA, and it happened in one of these, all the documents that Snowden made public. It appeared clear that there were some devices that had been tampered by NSA. Okay, I mean, it was tampering the cryptography devices from inside, and they were certified by NIST. So NIST is the National Institute of Standard and Technology. NIST was saying these devices are good for you to use them for cryptography, but they have been tampered by NSA. So you were using them, thinking they were secure, but they were not. And this is the only reason why this happens is, well, then, I mean, then companies where RSA was, for instance, which is a company for cryptography, they were telling, please stop using these devices because they are insecure. And the customers say, but they were secure before because they were certified by NIST. Well, they were not. Okay? So this is a problem with certification. I mean, when you buy something from a provider and you are really care about security, you always put some trust in the provider. Okay, here people were putting trust in NIST, which is, I mean, I trust NIST. I'm sure they tried to do their best, but of course the problem is that NSA were tampering the devices. So the idea is whether you always need some trust, okay, or whether you can somehow certify that some devices are secure, and this is where this black box approach is very useful. Okay, and I always use this joke because I think it's very good for all the stuff. So you can understand that trust and certification is a very critical issue. So this Dilber who goes around and he looks at the random number generator. This might be bought from NIST and certified by NIST. Okay, well, I mean, why not? And this is a problem, no? Are you sure that's random? But this is a problem, no? You can never be sure about randomness. But of course, I mean, why not? I mean, the probability that a random number gives this sequence is the same as any other sequence. Okay, so C9999 for you doesn't mean anything. So how can you certify that something, for instance, is random? Well, okay, I mean, using this device-dependent approach, now I will tell you briefly how we could certify that things are random. Okay, so and the idea is the following. So usually the standard approach when you want to buy a random number generator, you go to the provider, and this is something that you can buy in companies. Okay, you can go and buy a random number generator. Why? For instance, typical example I use for my talks as well. You have a virtual casino. Okay, so you come to me, and I know that you have a virtual casino, and you want a random number generator. I'm Catalan, and I like very much money. So before you come to me, I have a very good random number generator. I generate many numbers, and I copy them into a classical memory. I put this memory into a box, I paint it in a fancy color, and I write quantum random number generator. And I'm selling this to you, and I charge you twice because it's quantum. Okay, so you go, this looks pretty quantum. So you start generating numbers, and because since I generated these numbers before you came to me with a very good random number generator that I have, you pass all statistical tests. So you think, this is a really nice guy, okay? And then you start using your random numbers in your virtual casino. But of course, the numbers are random to you, but they are not random to me. Okay? So I get all your money because you trusted me. Okay. So what you have to do, you have to come to me, and you are not going to ask just one box, but you're going to ask two boxes. Okay? And then you take these two boxes, and you see that they violate Bell Inequality. And now what you can see is that from the observed correlations, from the amount of Bell Inequality violation, you can deduce that these numbers have to be random. Okay, why? Because if I had a perfect copy of these numbers, this would mean a local hidden variable model for your data. But since your data violates Bell Inequality, I cannot have a local hidden variable model for your data, so I cannot have a perfect copy of your data. Okay, this is intuition. But basically, the problem we solved was the following. If you see some boxes that violate a Bell inequality, and you assume that these boxes are quantum. They might be qubits, qubits, whatever, but you see that they violate a Bell inequality because it's something that you can self-certify yourself by pressing buttons and observing outputs. Then, by how much I could fix this output. I can do whatever I want with these boxes, but I cannot break quantum physics. So there is something there generating this data, which is quantum. You don't know what it is, you don't care. But you know that it's something quantum that gives these correlations that you can certify. And then in this paper, we provide techniques from a Bell inequality violation, how you can bound the randomness in your data. Okay, so this is the inequality that has appeared during all the talk, this CHSH. You remember the local bound was 2, so here this is classical physics. Here you have the quantum non-locality regime. You remember my picture, this quantum region that was above classical physics. And you can see here at the region of no violation, my predictability is 1. Well, not surprising, okay, because here's the classical world. But as soon as you enter the quantum region, my predictability goes down. So if you think of me as the enemy, the provider that wants to cheat you. So I cannot fit your output by totally, okay? There is an amount of unpredictability. And at the point of maximal quantum violation, the predictability is 1/2, which is basically no predictability. Okay, I can flip that one and get the result. And the nice thing is that here, and if I have time, I will tell you how, all this region is simply impossible with quantum physics. So if you were able to observe this amount of inequality violation and predict my outputs by this amount, this would mean that you would be using things that are not possible in classical physics, in quantum physics. Okay? So this is what you can do. So you can come to me, you can buy these boxes, you can trust that I won't be able to use non-quantum effects, and then you can certify that something is random from the Bell inequality violation. Okay, now this is good, okay, because once you have certified randomness, you can use them, for instance, for cryptography. So what is cryptography? Cryptography is the art of sending private information. So me, I want to send a private information to my wife, and we do it in a way so that nobody can read this information. But we already have cryptography. I mean, we encrypt the information in our daily lives because it's something essential, no, in our information society. So the first thing I want to say is that quantum cryptography, the main point I find is that it's something different from classical cryptography. So classical cryptography is based on a computational assumption. You base the security on computational assumptions. So you assume that the enemy that is trying to read your information has the computational power that is limited. Okay? Well, with this assumption, you have some protocols. I think that there are some problems with this assumption, and one of the main problems is that the standard approach to classical cryptography uses some problems that are easy for a quantum computer. Okay, so if the eavesdropper had a quantum computer, the eavesdropper could break this classical cryptography. Now, in quantum cryptography, you do something completely different. You don't base security on computational assumptions, but on physical assumptions. So your devices are quantum, and whatever an enemy does, this enemy cannot break quantum physics. And this is why the protocol is secure. Okay, so this was very good, and people were writing papers, and they were saying that quantum cryptography is unbreakable, and blah, 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 and funding. But some years ago, there was this guy, Buddy Makarov, with some other people. They bought some quantum cryptography products because you can buy quantum cryptography, and they hacked them. Okay? And of course, people working in quantum cryptography saying, I mean, you're a liar, no? Because you said during many years it was unbreakable. Okay, I mean, well, he looks like a quantum hacker, and this is why maybe he had this idea. But then you can ask, but I mean, in the end, this Makarov attacks and some others, this looks very good because I think if you think about any cryptographic field, it's never mature if you don't have any hacking. Okay, so if you don't have any hacking, you cannot say that a cryptographic field is mature. So why did they break this? Well, of course, what the hackers did, they didn't break the principle, but they broke the implementation. So what is quantum cryptography and why is it secure? Well, it's secure because it's said to be secure because there is a mathematical proof telling you that it's secure. And of course, and this proof is based on quantum physics. Of course, Makarov didn't show a mathematical mistake in the proof. Neither he showed that quantum physics was wrong. He did something different. So what was what Makarov exploited? So if you look at the theory, the security proof that you use to claim that quantum cryptography is unbreakable, the security proof tells you several things. So for example, it tells you if you want to run a protocol, you have to prepare states that live in a Hilbert space of dimension 2, and you have to make these measurements, and blah, 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 and with this, you can make cryptography. Now you go to the companies or an experimental lab, and you say, why don't you prepare me something living in a Hilbert space of dimension 2? Well, this may seem something trivial, but I think preparing something that lives in dimension 2, I think it's impossible. Okay? You can guarantee that with very high probability, you are only using 2 levels, 2 degrees of freedom. But how can you guarantee this? I think it's impossible. And of course, what the companies do, for instance, they tell you, well, I don't know how to do that. I will use a laser and I will attenuate. This is what I will use to produce my states. Of course, I wouldn't say that an attenuated laser source is an object living in a Hilbert space of dimension 2. I think nobody will buy this. Okay, and of course, what they do, then they measure the light, and they use, say, single photon detectors. Well, a single photon detector is not a spin-1/2 measurement. So here there is a mismatch between what the theory predicts and what the experiments do. And this is precisely the mismatch. So quantum cryptography was secure here, but the implementation was there. And this is what Makarov broke. Okay, so he broke the implementation, but not the principle. But somehow it seems that here, if you want to make something that is secure in theory and in practice, you have to avoid this mismatch. And the way of avoiding this mismatch is by making protocols in this scenario. Because if you base your security only on the correlations, you go to the lab, you see these correlations. And then no matter what is inside the box, it will be secure. Okay, you don't have to, your security won't be based on the fact that you prepare Hilbert space of dimension 2, 3, spin-1/2 measurements, or whatever. There is something there, but this mechanism is enough for me to have these correlations. And then the security proof tells you that these correlations are secure. Okay, I will skip this. Okay, so this is a solution to the hacking problem. So device-independent quantity distribution. You go, again, the idea is the same as for random numbers. We want to exchange some private information. We go to the provider, we buy some boxes, and these are 2 black boxes. We test them, and hopefully, if we see some correlations that are good enough, we can use them for cryptography. And again, if you want to make sure that this is potentially secure, these correlations have to violate a Bell inequality. Because if we don't violate a Bell inequality, there is a classical explanation for these objects, and a classical explanation is something that for which an eavesdropper can have a perfect one. Okay, so that was, how much time do I have? More or less half of my time? I have 15 minutes left. Okay. Okay, so this is some of, I very briefly told you about how to use this Bell inequality, which is a result of obtaining quantum foundations to make applications in quantum information theory. And now somehow I will do the opposite. Okay? So I will use concepts from quantum information theory to say things about quantum foundations. So this is the second part of my talk. And here I will come back to, where is it? No, okay, to this. Go back to this. Remember, to this picture, okay? So in my previous explanation, I told you, if you go to a lab, you can always make measurements of particles, and you will observe some correlations. And we know here that we believe that we are at this point, okay? So we know that classical correlations do not explain everything that we see, because there are quantum correlations, violation of Bell inequalities. But I mean, we don't know whether this is the ultimate limit of correlation. Okay? There could be some supra-quantum theories that could give some other correlations. So before Bell's theorem, I would say that everybody thought that the way devices could be correlated were the way predicted by EBR models. In fact, Bell inequalities, I was told, and I never checked, that you can find some Bell inequalities in some papers by Boole. Okay, so he was thinking about how things can be correlated, and of course, I mean, Bell inequality is something very trivial. I mean, you simply think with your common sense about how things could be correlated. Now we believe that this is the ultimate limit. Well, this is the known limit for correlation. Okay, but now, could there be any supraquantum correlation? What people thought, for instance, Popescu and Rowley, they thought, oh, maybe a way of understanding why we have only quantum correlations is related to the fact that if we see something beyond quantum, then we are violating something dramatic. Okay? For instance, as soon as we see something that is beyond quantum physics, maybe the correlations are so strong that I can use them to make faster than light communication. But they prove that this is not the case. Okay, this is why you can have this region here that is supraquantum, but does not allow you to make any faster than light communication. So now people are trying to understand why this region, whether this region is possible, and if it's not possible, why not? And they're trying to understand whether we can have correlation beyond quantum correlations or not. So this is the question, okay? Now I will give you. So this is the question. Imagine you have some correlation. So you have an experimental lab, and a PhD student goes and. Yeah, okay. Thank you very much. So you have an experimental lab, and you have also a PhD student, and the PhD student prepares a state of two particles and makes two measurements here and two other measurements here, like in the standard Bell test. And he just sees these numbers, computes the probabilities, and at the end of the day, he comes to you with these numbers. Okay, so what do you do with the student? You fire him, you write a paper. Well, I mean, these numbers, there is nothing wrong in these numbers. Okay? These are just probabilities, they sum up to 1, positive. Okay. So the question is whether, for instance, these numbers are quantum or not. So by this I mean whether there is a way of writing these numbers as a trace of a quantum state with a measurement for the first particle and a measurement for the second particle. Okay. Well, do you want to make a guess whether they are quantum or not? Well, they are not. Okay. So if the student sees this number, then the whole quantum physics is wrong. They look innocent, but they are not. But you can understand that this problem is difficult because if I give you this number, how can you check that they are quantum? Well, you will tell, oh, I take a state of 2 qubits and I try to see if I can put a state of 2 qubits here and measurements of 2 qubits so that I can get these numbers. And you will see that there are none. And then you say, but maybe I'm measuring a system dimension 3. How do you know? Okay. Then you try and you see that there are none. But then you have to go dimension 4. Okay. So you have to explore in principle all possible quantum realizations. And this is why the problem is difficult. I mean, there was some previous work by Silson on that. Okay, so because remember, this is in a way the logic is the same as Bell Inequalities. The beauty of Bell Inequalities, it was a test that falsified all possible EPR models. Okay, before Bell, I mean the decision of the EPR model was more or less a discussion for coffee breaks. Okay, so you were not able to find an EPR model for quantum physics, but this was not a proof that there was not. Okay, so here this is an analog. This would be some sort of quantum Bell Inequalities. You see data numbers like this, quantum physics is wrong, and there are super quantum transitions. Of course, nobody has seen anything like this. Okay, I'm not claiming, but I mean, these at least we have tools to certify that something is wrong. Well, for that, well, the problem is difficult because, as I told you, in principle, you have to explore all possible quantum realizations that are compatible with these numbers. But we gave a solution in this paper some years ago with Quest, who was one of my PhD students, and Pironio, who was a postdoc at that time in my group. And basically what you do, you run some sort of test, and if you want in a pictorial way, what these tests do, they approximate quantum correlations from above. Okay, so this is the first test, this is the second test, and blah, 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 blah. So basically what you do, you give me some correlation. The student goes to you and gives you some correlation. Okay, and now you run the first test. And the good thing is that it said you can do it with a classical computer. And then you see if the point is inside or outside the set. If the point is outside this first set, of course, that's how quantum correlation. This is what you can say, they are not quantum. If it's inside, you don't know. But then we have a second test that is computationally more demanding, but you can still run. If it's not in the second set, it's outside. Of course, it's not quantum. If it's inside, well, you don't know, so you have to run the third one. Well, in the end, you have to, I mean, this is only asymptotically convergent. Okay, you have to run an infinite set of tests to say whether yes or no. But the good thing is that it detects points that are outside. Okay, so so it can tell you, for instance, that these points here are not quantum. Okay, so for the first time, you have tools to prove the non-quantumness of some data. Okay, so this is the last thing I wanted to say. Well, okay, so we have tools to somehow understand this boundary. And as I told you, another question, I mean, this is now, okay, we have tools to understand this boundary. We know how to use the region here to make protocols for random generation and cryptography. And as I told you, Popescu and Rodlik in a previous paper, they said, well, maybe there is a reason why these correlations are not possible. Okay, so we don't see them. Maybe we should understand why we don't see them. And what's the only reason we can find now? Well, because we don't know of any Hilbert space where we can put the trace and collect the things so that they give this correlation. Of course, the thing that some correlation violate quantum physics for many physicists, that's a pretty convincing reason to believe that this correlation are not possible. But maybe you want to find another, I don't know, less, a more operational or I don't know, another point of view, okay? And they started thinking about maybe there is a principle that explains why this correlation is not possible. At the moment, the principle is they violate quantum physics, okay? And this meaning that there is no state and measurements in a Hilbert state that give this correlation. But maybe you can find another explanation for that. They thought about no signaling, faster than light communication, but they saw that that was not enough. So people are trying to understand why we don't see these correlations. And especially people coming from quantum information theory. For example, there is a paper that I like it a lot by Wim van Dam. Actually, it's a result in his thesis. And what Van Dam proved was the following. So imagine I want to come here and to give another talk, because you like it so much, mine, that you want to see another talk by me. And then I will have to see a time to come here with Armando, and we have our agendas. So what we have to do, we have to agree on when to come. Okay, and we are by phone. And then what I will say is, well, I cannot make it on Monday. What about Tuesday? And he will tell me, well, Tuesday I cannot. And we'll have to exchange some communication. Okay? So this is the context of communication complexity. We have to compute a function of our agenda, and this requires some communication. Okay? And you understand that the busier we are, or the more complex our agendas are, the more communication we will have to exchange. Okay? So we expect that communication complexity is non-trivial. So we can make the problem difficult so that we need to exchange a lot of communication. So what Van Dam showed was that if these correlations were possible in nature, then communication complexity would become trivial. So just by exchanging one bit, we could find a place in our agendas, no matter how difficult they were. Well, this seems like crazy, no? But at least for people working in information theory, this is like, you cannot believe in something like this. So now you have another reason to believe that these correlations are impossible. If they were possible in nature, you could do things that you don't expect to happen, like rendering communication complexity trivial. And now people became crazy and they started thinking, oh, now we have to understand how to get down from here up to there with an information principle. And then people propose principles. I also propose an information principle trying to understand. But of course, I mean, proving that some points here, supraquantum, violate a principle is relatively easy. To prove that you go down up to the quantum region, this is a nightmare, because nobody has done it. I mean, in some cases, but usually you cannot. And actually what we did in a recent paper, what we proved is that this might be very difficult, because we have found a set of supraquantum correlations, so larger than the quantum set, that satisfies all the principles that have been proposed so far. So from an operational point of view, whether nature is quantum or as we call almost quantum, doesn't seem to make any big difference. And okay, we invented it because we had some intuition, and I'm not going to tell you about the definition of this. But okay, we saw that there is another set of correlations that could be, at least with our present knowledge, as plausible as quantum correlations. Of course, we don't have a theory for that, but they don't violate, they have non-trivial communication complexity, they don't allow any faster-than-light communication, they satisfy all the principles that are being proposed so far. Okay. And what was interesting is that we started talking about this to people working in connection with quantum gravity, so something that is called the coherent history approach to quantum physics, with a quantum gravity motivation. And these guys had defined some correlations in their theory. And when talking to them, it happened that what they had was exactly what we had. So we're pretty surprised by this. I don't know if this is an accident of nature, or probably it is, okay? But this is something that we should understand. So this was a result that was proven in this paper by this people. So it's not our result. So the interesting thing is that in our case, coming from an information point of view, we propose a set which is supraquantum, slightly supraquantum. We call it almost quantum. And for us, it was interesting because it was satisfying all principles proposed for quantum correlation. And in their formalins, they had another way, which is, I can tell you slightly more details because it's not my field, but they had found another set and it happened to be the same. I think this is worth exploring. Okay, so this was long and dense, and so it was some sort of exploration about some of the things that we do in my group where we deal with boxes. Okay, and the reason why we like these boxes is because you can say things that are practical, like cryptography, random generation, but you can also say things that are more on the foundational side. So the messages I wanted to give you were several. The first one is that if you want to do these protocols in this black box approach, where you don't want to put any trust in your provider, then you need to see non-locality. Again, because you don't see a Bell inequality violation, there is always a classical explanation for your data. You cannot do anything beyond classical information theory. So the question is to understand what you can do in this region. Okay, I didn't say, but this is theoretically very interesting, but experimentally it's challenging because you need detection loophole-free violation. I didn't discuss this, but I mean, from an implementation point of view, you have to face some challenges. And also, I briefly told you why this also sheds new light on quantum foundations, okay? Because now you have another way of understanding quantum correlations and even understand quantum correlations from above. Okay, this I can skip. So this is just the conclusion. Okay, so these boxes, this marks some sort of intersection between protocols and almost engineering and computer science concepts and from the quantum foundations concepts. And perhaps you can also use these techniques in a quantum gravity. Well, this is very speculative what I'm saying here. Okay, but perhaps they can also be used in other contexts more in relation with quantum gravity. And the last thing is an advertisement. So at ICFO we have a program for postdoc positions that is mostly oriented to senior postdocs, and it offers good conditions for postdocs in Spain. And the next deadline will be December. I want to conclude this. Thank you very much.
Questions?
I have a question. I understand that you have a criterion in order to single out whether a certain correlation is a quantum correlation. But you always, in the discussion, you introduce also this concept of almost quantum correlation. Does it mean that you have a non-ambiguous criterion in order to quantify the entanglement?
Well,
because in certain times that was a discussion that was present in the literature. This way, this other way to quantify.
No, okay. No. So the motivation is different. So whenever you pronounce the word entanglement, okay, entanglement is a concept that is in my language is not device independent. So usually entanglement is something that you want to estimate the entanglement of a state. So if you wonder what's the entanglement of a state, you already have in mind a state and a Hilbert space. Okay. So here is some sort of quantum physics with no Hilbert spaces. So I'm not fixing any Hilbert space structure. So I know there is a Hilbert space, but I don't know whether it's qubit, Q3, whatever. I have a quantum black box. So I don't care about entanglement.
It depends on your device.
No, it doesn't depend. This is why it's device independent. The only thing I'm assuming is that I have a device that cannot break quantum physics. What is inside my device can be a qubit, qubit, again, whatsoever. Okay. This is why the concept of entanglement does not play any role here, because it's a concept which is, if you care about entanglement, you're writing a state. Whenever you write a state, you're writing a matrix, and you're writing a dimension. This is a quantum sort of information theory or quantum physics with no. I mean, the Hilbert space is behind the scenes because I'm assuming that there is a Hilbert space in the box, but I'm not making any assumption about the Hilbert space. I'm just assuming that it exists, but nothing about the dimension.
Okay. Thanks for the clarification.
So, I was thinking about the cryptography, because by computing these correlations, measurements, you can certify, can you certify that there is no eavesdropping
Well, this is the idea. So we go to this is the idea why, and this is why they are useful for certification. Okay, so you and I, we can go to the provider and we ask these two boxes. Okay, and these two boxes, in the standard approach, like you go to the company, they tell you, we prepare a qubit. You have to trust them. Okay, you are never going to open the box and see that there is a laser, and you're not going to make any money. Now we can go and we ask simply a device where we can press two buttons. You're never going to do it like this practically, okay? But imagine that you can. And then I have my device with two buttons, you have your device with two buttons. And we keep pressing the buttons, getting the results, and counting the frequencies. Okay? So I say, well, this time I measure 1 and I got result 1. What did you get? And you tell me. And then we count the correlations. And only from this observed correlation, we should conclude whether we can use this for cryptography or not. And there are some mathematical proofs that show you this is possible.
You mean for any kind of eavesdropping?
For any kind of quantum eavesdropper. So this eavesdropper can do whatever she wants without violating quantum physics. Okay. So this is an assumption. Yes. Of course. Well, what you prove in the cryptography, basically from the correlations, from the amount of non-locality that we see, we know how much information the eavesdropper has. And we can use this to extract a secret key, and this is more technical. So yes, we can exclude the eavesdropper from the picture, only from the observed correlations.
Okay, if there are no other questions, I think we have to thank all the speakers.